recording going? Good. Recording is working, and now I'm going over to, oh, that's going to be interesting. Let's see if that works. Screen one. Ta-da! Okay. Ladies and jelly beans, can you see my screen? That would be absolutely amazing. It works. Yee-hee. That's cool. God, I'm so glad. And absolutely right. Don't forget to record your attendance. Thank you very much, Bernardo. That's absolutely brilliant. Yes, I can see that there's a little bit of lag. I apologize for that, but I hope it's not too bad, actually. Aha. There is, let me just quickly check. Okay. I need to turn off the sound on the different monitors, because otherwise you go totally bonkers. Let me turn that off as well. Is it off? Yep, that's off. Okay, good. What do you mean you don't understand the stuff? Honey, and confused you all. Well, I mean, isn't that the stuff that you put in the milk? Huh. Uh-huh. Oh, okay, I see. Oops. Excuse me. That was the curry that I had for lunch. Then he said, what? I mean, I don't have anything to do with that practical. I'm terribly sorry.
What's that?
So please don't ask me.
Basically, I'm in a lecture. Oh. Yeah. Is there any chance you could walk to me and then we'll get the stuff after?
Oh, no, fuck that. Sorry, I'll make it, no worries.
What do you mean?
Sounds like a really good idea.
No, but we'll get the stuff after. You can't take all of it. Don't be silly.
I can't be asked to go back to the car. So long.
But aren't we going to go and get food later? Anyway.
Yes, absolutely. Domino's.
We are going to do that.
Exactly. So why don't we just not...
I'll bring half the stuff.
Bring the stuff that you need, like your stuff, like clothes and stuff, and then we'll get the other non-essentials after.
Yeah, now it's getting interesting.
I can't say what they are.
Oh.
Oh.
Fine. I'll come. I'll just do my lecture after.
No. You got to let go. You said you got lecture. We're not free.
But.
No, you got lecture.
I'm so
what if I drop my leg?
I would like to start.
No, it's fine. I'll make it.
I want to know more.
You sure?
Yes, I'm sure.
Yeah.
Okay.
Alright, I'll see you in like 2 seconds. Not 2 seconds. I'll see you in about like 10 minutes by the time I get there. Do it.
Okay, bye. Love you, bye.
Oh, how sweet.
Nie przyszłam na czat.
It's so sweet of her, isn't she?
So there's this girl. We're on the what's the actor? I'm in the lesson, and this girl, she unmuted herself to call. She called her boyfriend, and she was telling him all.
That gives me strength. Oh, hey. Okay, hey guys, shall we get started before I wet myself? Anyway, let's get started. So, most wonderful afternoon, everybody, and welcome to this session. My colleague, Dr. Chris Mulligan, and I had a chat last night about some aspects of this practical. And we decided it might be probably a good idea to do a quick revision of graphs and how to get data from standard curves. If that is something that you don't have any problems with, then, well, stay with us. Maybe you learn one or two things that are new to you. So I want to talk a little bit about correlation and standard curves with you today. Please don't forget to do the Moodle attendance. The first thing that I want to discuss with you is I had a very interesting discussion last year with some learned colleagues about how actually to plot data. And you would assume this is something that everybody knows, but not everybody knows that. So what we usually, when we create graphs or plots, we usually have a y-axis, and I can't draw straight on this tablet here, but hopefully you get the gist. So we usually have a two-dimensional plot, and I'll show you how to do that in Excel later. And what we plot on the x-axis, so that's the x-axis, of course, that's the y-axis. And what we plot on the x-axis is the independent variable. Let me write that down. That's the independent, independent variable. The independent is this thing that you, the researcher, has control over, that we can sort of easily manipulate. So, for example, concentration of glucose or other things. So this is the independent variable. And you can plot the independent variable, or sometimes it is necessary to also plot a transformation of it. Transformation of the independent variable. So what is a transformation? I will show you examples where we don't plot the independent variable, but we might plot the logarithm of the independent variable, or we might plot 1 over the independent variable. The independent variable is always on the x-axis, because that is what we have control over. There are not very many examples where you don't have the independent variable on the x-axis. I will show you an example for that next term when we do enzymes, but that is really the big exception. So what you plot on the y-axis, you plot what is called the dependent variable. Dependent variable. This means this variable is dependent on the independent. So this is really the independent variable determines then the independent. Oh, sorry, let me say that again. The independent variable determines the dependent variable. And again, we might want to plot the dependent variable as it is, or we can also use some transformations of it. And again, I will show you, for example, a logarithmic transformation for the dependent variable, or when we do the enzyme stuff next term, I will show you that sometimes we also plot 1 over, and so an inverse or reciprocal dependent variable. So this is the convention. And as I said, there's very little leeway. Independent is x, dependent is y. And so that's really important. Now, obviously, you have in the virtual honey practical, so the y-axis is always the dependent variable. That's right. So what you do in this virtual honey practical is obviously you are taking some glucose concentrations, or I've just made up some numbers here, and you create a standard curve. And again, let's repeat standard curve. In this case, you have some known concentrations. That's the independent variable. So these are the concentrations here, which you would plot on the x-axis. So these are the concentrations, and they go on the x-axis. And these are the concentrations you have control over. So instead of, say, 8 millimolar, you could say, I just use 10 millimolar or something like that. So you have full control over the data that are here on the x-axis, on the independent axis. I put transformation into brackets because it's something that might be optional. We don't always have to do a transformation, but we can do it, and it changes nothing about the order or the way we plot things. So we plot the concentration, and in the practical, if you were to do it in live and in color, you would measure the absorbance of your different glucose concentrations in the spectrophotometer. And actually, I don't know whether this is glucose concentrations or something like that. That just should show you the principle of the how this actually works. So here on the y-axis, we would put the absorbance. What's the unit for absorbance? What's the unit for absorbance? Yep, you're absolutely right. Absorbance doesn't have a unit. What's the unit for the concentration that I use here? Micrometers, no. Concentration is millimolar, because it's here, the millimolar, that's the concentration here. So this would be the concentration, millimolar. Okay, now, how is this going to look like? Let me just get rid of, we'll keep it on. How does this graph actually look like when we plot it? And I'm using Excel here, as you can see. You all should have access to Office 365, because otherwise you would not be able to use Teams. So you should have access to Excel. And Excel, some people really sort of think it's baby stuff, but Excel is incredibly powerful if you know what you're doing with it. So let's have a look how our data actually look like. And in order to draw the appropriate graph in Excel, we go to Insert here in the ribbon, and then we go to the Chart section, which is here, and we would use the one that has these bubbles in. That is what is called a scatter plot. Do never ever, under any circumstances, use the line plot. Always use scatter plot. This is this one here, right? So in order to plot our data, what we do is left mouse button clicked, and we highlight all the data that we want to plot. We go to Charts, Scatter. And look at that, we get a really nice plot. Obviously, we would need to label things a little bit. So here we would have the concentration in micromolar, and here we have the absorbance. So that would be our plot that we have. And this is now our, well, this would be the standard that we have with known concentrations of glucose. That's our standard here. Now, if you did that with graph paper, the first thing that you probably would do is you would try to do a line of best fit. Am I right or am I right? Biomed engineering students don't do this this is a practical for BI 300, and I don't think you guys do that. So don't worry. What I just show you here is a general scheme on how you use standard curves to get some data, which is actually useful for the people who have done this practical. With absolutely, you can use R if you know how to use R. That's absolutely fine. But not many people know how to use R, so Excel is more commonly used. But if you know how to use R, if you know how to use the different packages, then please do feel free. I don't want to curtail you in any way. So what we can do in Excel very easily is to do a line of best fit. And the best way is to just simply choose one of the points and left mouse click on the point. So what you see is that all the points are now sort of X'd. They have an X that indicates they all have been selected. And now with the right mouse button, one click right mouse, So right mouse, and you get to a menu that says Add Trendline. Can you see that here? Add Trendline. Just simply click on Add Trendline. And let's see what happens. Oh, look at that. How cool is that? We get a line of best fit, actually. And Excel calculates the best fit line. What you see here, this dashed line, is the line of best fit. So you don't have to do, sort of eyeballing and have to stress about to get the best line, the line of best fit. Even better, what you can do is you can actually get the equation for the line of best fit. So if you look at the area here, which is just above the meeting, the team stuff, what you can do is you can say display the equation on chart and display the R squared value on chart. Should the line of best fit be dotted or solid? To be perfectly honest, it does not really matter. There is no convention, and it's not an issue. And display R squared value on the chart, and we will discuss what the R squared value is. So what Excel does, it calculates for you the equation of the line of best fit and this R squared value. And this is our line of best fit. Would we have to exclude outliers first? Angelina, that's an excellent question. Do we have outliers here in our in this plot? It's really interesting because with a two-dimensional data, as these are, it is not that straightforward to actually figure out what is an outlier. Is this here? Is this point here? Is this an outlier? Or is this just simply a little bit out in terms of measurement? Probably it is challenging actually when we do what this method actually is called linear regression. And in linear regression, it's not always easy to figure out what is an outlier and what is not an outlier. When do you do that? I think in the final year, I will show you how you can determine outliers, but it is not for the faint-hearted. So I would leave this point in here. So outliers would generally be data points that are away from the trend line or the line of best fit. And that are really badly away. So if you had, for example, a data point up here, then I would say, this probably looks like an outlier. Can you use median and IQRs for that? No, you shouldn't. In this case, no, you shouldn't. There are other methods, but they are a little bit more advanced, so I'm not going to bother you with that. There is another thing that we need to be aware of, and that is actually what is called an influential point. Influential point. An influential point is a data point, x and y, that is close to the y-axis, but that is sort of pretty much away from lots of, or most of the other data. So one could say this point here is quite away from the next point, which is this point here. So this could be an influential point. And I will show you when we do the enzymes next term that influential points can be an absolute bugger to work with. They can be absolutely horrendous if your graph has influential points, because if you just have a slight change where the point is, then your curve or your line would be very different. So that's, that can be quite a pain. If you actually want to calculate what your gradient is for your line of best fit, does anyone know the general equation for a straight line? What's the equation for a straight line? Lovely. Yeah. So y equals mx plus c. So m denotes the gradient, and c, of course, is the intercept. So that's the gradient or slope. If you want to calculate the gradient and you don't want to use the data here, you can do that in Excel. It's very simple and straightforward. I'll show you how to do that. For the gradient, you tell Excel that you want to do something. So you start every command in Excel that's a little bit like Alexa or Siri. Is Excel do something, that's the equal sign, equal, and then you start typing, and the gradient in Excel is called slope. So you start typing slope and you see it comes up with a suggestion. You double click on that, and what you do now is it tells you what it wants you to do. It asks you for the known y values. Now we plotted the absorbance on y, so we just simply left mouse clicked and we highlight all the cells. You can easily take the label here, the absorbance, that's not a problem. Excel is smart enough to deal with that. So absorbance, comma, and now we put in the known x-axis, x values, and again, left mouse button clicked and we drag it down and we have our data. We close the bracket and press enter, and we have our gradient. And we can do the same thing for the intercept here. We just start with equals and then start typing intercept. Oh, look, it comes up with a suggestion. Double click on it and it asks us again the known y values. So we do exactly what it asks for. Left mouse button clicked, absorbance, that was the y, and the x values, again, left mouse button clicked, drag it down, close the bracket, and we have 0.0129. It gives you a little bit more decimal places than the equation here, which sometimes is not too bad a thing. So we can even calculate the gradient and the intercept for our line of best fit, even if we don't plot the line here. What is this correlation? Now, correlation tells us, so the correlation correlation is a measure how good the fit is a measure of the fit. And basically the R squared value that we have here, so in this case, let me write this down here, R squared, the R squared value, this is often referred to as Pearson's correlation squared. So that's the Pearson's correlation factor. The R squared value tells us how many Y values are explained by the X values. And it gives us sort of a percentage. So here the R squared value was, I think, 0.98. Was it 0.98? Yeah. Which means 98% you can use, you have 98% of our Y values can be explained by the X value. And obviously there are slight differences, and these differences account for these remaining 2%. Now an R square value, okay, where does it say? It says here R squared 0.9825. Can you see that? So it basically tells us 98% is a fairly good correlation. I would say actually a very, very good correlation. Very often you will find also instead of the R value, you might find the R squared value, you find the R value. The R, again, that's Pearson's correlation, but not squared in this case, gives you also quite some information about the plot. And I come back to that question in a moment, Amy, don't worry. The R value is again sort of, it's the square root of the R squared value. And it tells you, it gives you more information about actually your plot. Because what we have got here is we have what is called a positive correlation. We have a positive correlation, and my handwriting is absolutely abysmal, so I apologize, but that's the new tablet. In a positive correlation, X and Y values move in the same direction. Move in the same direction. So if we increase the X values, like here, then we also see an increase in the Y values. So that is a positive correlation. And in this case, our R value R would be larger than 0 because it's positive. Oh, sorry. R is larger than 0. We can also have a negative correlation. Negative correlation. And in this case, X and Y values move in opposite directions. So how would that look like? Let's draw a graph. Here we have the Y, here we have the X values. So the larger our X becomes, the smaller Y becomes. So this would be something like that. This would be a negative correlation. And in this case, R would be smaller than 0. Oh, don't worry about that. We will come to that. Maybe not today, but next week we will come to causation and lurking variables and all these funny things. So an R value is between negative or positive 1. What happens if an R value is 0? How do I produce an R value that is 0? What would the graph look like for an R value that's 0? There's no correlation, and the line is horizontal. So my data points might be sort of all over the shop, like that. So here in this case, it's not exactly how I wanted it. Let me just see if I can get this nice. So that would be R equals 0. There's no correlation, and the data are all over the place. An R value of positive 1 is all the data are exactly on all data on the line. And R value of negative 1 is also all data are on the line of best fit. But in this case, an R value of negative 1 would, for example, look like that. All the data are perfectly lined up on this. So in this case, R equals negative 1. Does that make sense? Are you happy with that? Yeah. What is a good correlation coefficient? A good fit, I think good correlation Good correlation is everything where we have an R value larger than at least 0. Let's say 0.9. I think there is then a very good correlation. So a negative R value means a negative correlation, and X and Y move in different direction. And R value of positive number would, for example, be this line here that we have here, where X and Y move in the same direction. Okay? And for the intercept, again, you just simply equals intercept. Okay, happy with that. Now, what can we do with this standard curve that we have here? Oops, get rid of that. With a standard curve, what we can do is we can take measurements of our sample here. So I've taken some measurements of samples. And what we can do is we say this is the absorbance of, let's say, a sample of the first sample. And what we can do is we can look at this absorbance. For example, that would be here. And in order to find the corresponding concentration, we just go to the right, like that, when we hit the line of best fit, and go down and try to read from the graph what the corresponding concentration is. So before we had concentrations and measured absorbances. Now we do actually the opposite. We have an absorbance and we try to figure out what the corresponding concentration is. So that is what we use a standard curve for. Okay? And we have, for example, different samples. So very often people say, right, what we do is we just take the mean of these samples. We take the mean of these samples of our readings. And we just take this mean. For example, the mean would be this one here. We go over there and this. This is not how you do it. Do not take the mean of the samples of the absorbances, because that is strictly not the way you should do it. The correct way of dealing with that, let me see if I can move that out of the way. The correct way of dealing with it is the following. Let me just simply remove this first. You take every single measurement, absorbance measurement, every single one, and you determine the corresponding concentration for it. So you do this one for measurement 1. Let me highlight this. So this is the first measurement. And from the graph, you determine that, the concentration. That gives you the first concentration. You then take the second measurement. That's this one here. It's a little bit larger. Something like that. and you determine the second concentration. And the third measurement, that's a little bit smaller, and I have exaggerated it here so that you can see it properly. This would be your third measurement here. Yeah, so that is this one. This is this one, and this one is this guy here. If you have several samples, then again you can put them. You look them in this way. You can always determine your three concentrations. So you determine the three concentrations. So concentration 1, concentration 2, and concentration 3. And from these three concentrations, from the concentration that you determined, from this you calculate the mean and the standard deviation. Not from the absorbance, you calculate it from the concentrations that you've determined. Okay, does that make sense? Not the absorbances. Leave the absorbances alone. You use the concentrations that you determined from your standard curve. James, fantastic question. Is there a way, instead of faffing around, with these curves, is there a way to get Excel do that? And you might have guessed, yes, there is a way. Because all we need, let me make this a little bit smaller again. All we need is we use our superb mathematical skills and say, what are we doing here actually? Before we had X values, and we determined the corresponding Y values. So that's how we drew our standard curve. Now we have, if you like, we have the Y values, and what we want is really the corresponding X values. So what we can do is we can use our equation. We can say Y equals mx plus c, and we solve this equation for x. So what do? We bring the c to that side. That's our intercept. So we have y minus the intercept. And I put that in brackets. And I have then to divide the whole thing by m, by the gradient, divided by slope or gradient. So it would be y minus c divided by m. And with this equation, that's very easy. Let me just quickly copy these numbers here. I copy them, I put them down here. Paste the numbers, make them a little bit bigger so that we see them. These are our data. And I also copy the gradient and the intercept. I copy these data. Let's put them here, park them here. Again, make them a little bit bigger. Okay, let's do it like that. So all I need to do is I put in this as my y value. I have my intercept. That was the gradient here. That was m. And that was c. And all I need to do is put that into the equation. So the equation would be equals bracket. So this was my y value, for which I'm now looking for the corresponding concentration, minus this value, that was the intercept, divided by the gradient. Voila! Look at that. It spits out 15 point. I think there are a few figures too many. Let's reduce the figures. So let's say 15.2. Let's see whether this is what we would get. So for this one, 0.272. Look, if we go here, if we go from here to that, we would get something in the 15 range. Do you see that? But now we just let Excel calculate that with this equation here, which is just simply a rearrangement of our y equals mx plus c. Here we rearrange that so that we can actually get what's that? That we can calculate the concentration that would give us an absorbance of 0.272. Let's do that for this one as well. Equals bracket. We are going for this one minus the intercept divided by, I'm German now, divided by the slope. And we get 15.9. And let's do that for this one as well, because it's so much fun. Y minus the intercept divided by the slope. And we've got 14.6. Does it make sense? So we've got 3 concentrations for our 3 absorbances. Well, we can now very easily calculate the mean. We know how to do that. Equals the average. Oh, we just highlight this, bracket closed, and we would get an average of 15.3 millimolar. And for the standard deviation, let's quickly do that. Equals standard deviation, standard dot, because it's a sample, we use the S. Again, we highlight our data point, close the bracket. Voila, that's our standard deviation. Hey, tell you what, we do the standard error as well, because we know how to do that. That is equals the standard deviation divided by the square root of the number of observations that we have. That's 3. And that would be our standard error. So with this, very easily, these here are the concentrations. These here, let me just quickly write that down. These here were the absorbances, and these are the concentrations in millimolar that we've calculated. What you should not do is take the mean from the absorbances. That you shouldn't do. But what you do is you take the mean from the concentrations here. And that is what we just did. Is the standard deviation a little bit high? No, why? It's what we measure. And don't forget, these are data that I just made up, just to show you how you actually do that. So what you should have learned today is, well, it's a lot of stuff. How do you plot data properly? Independent on the X, dependent on the Y axis. You learned about the correlation coefficient, about R squared and R. You learned about positive and negative correlation. You learned how to find the gradient and the intercept in Excel and how to do a trend line in Excel. And you also learned how to actually calculate the concentration from a standard curve when you've got the Y values here. So these are the absorbances. And what we've done is we backwards calculated the corresponding concentrations. And we can then take the mean and the average. Does that make sense? So this is basically how you work with standard curves. Are you happy with that? I mean, time is up. Absolutely, yep. That's exactly how you do it. So this is, whenever you use a standard curve, this is how you can calculate your corresponding concentrations. At least this is how we teach it to undergraduate students. There's a little sort of caveat. This is sort of the easy way how to do it. The absolutely correct way is a little bit more mathematically involved. I might show you, or maybe not. Depends on how you guys feel about it. And how do you get the equation of the line? Again, this is, you simply click on one of the data points, right click, go to add trend line, and here you've got the display equation on the chart, or you can just simply calculate gradient and intercept with Excel, as I showed you. I have not had a lot of emails. Actually, I have had no email whatsoever from you guys about any topics that you want me to cover in a drop-in session. So therefore, I haven't set up anything. But if you want me to do a drop-in session, let's say on Tuesday, please send me topics that you want me to cover. If I don't get any emails from you guys, then I think everything is good and we don't need a drop-in session. So by, let's say, at the latest, tomorrow lunchtime, please send me emails about what you want me to cover, and then I'm very happy to arrange for a drop-in session next Tuesday, okay? Do they have to be BI 308? No, not necessarily. You can do also BI 300 of the material that I have covered. No, you would not necessarily plot a mean for the data on the graph because that would be just the calculated mean in this case. Okay, in this case, my job is done. I wish you a lovely weekend and enjoy your session with my lovely colleague, Chris Mulligan. So see you next week, maybe drop-in session or not, depends on you guys if you email me some stuff that you want me to cover. And I'm not going to cover everything that I have done. That's what the videos are for. Take care, be good, don't do anything I wouldn't do, and enjoy your weekend. You truly deserve it. So, how do I get out of that here? I need to stop the recording.